This is a lesson on VSEPR, valence shell electron pair repulsion. This says in small molecules, the geometry depends upon the orbitals, electron orbitals, spreading out as far as they can in three-dimensional space. VSEPR doesn't explain why, but it does explain the observation. So this is an observation-based thing. Small molecules only, which essentially is carbon based. So organic chemistry, really interested in the VSEPR, and eventually we're going to talk about hybridization. The main thing that you got to do is look at how many things are attached to a central atom. If there are two things, atoms, lone pairs, whatever it is, attached to the central atom, here's the central atom, it will look, two things separated in three-dimensional space will be 180 degrees, which is linear. They can be combinations of single bonds if it's beryllium, two double bonds for carbon dioxide, or a single and a triple bond carbon usually exhibits that characteristic. If you have three things attached to the central atom in three-dimensional space, that takes a 120-degree angle separation. So the bond angle is 120 degrees, and the name of this one is trinoplanar. Trinoplanar would be beryllium, or boron. Would be boron if it's a central atom, or a combination of two single atoms, or two single bonds and a double bond. If you have four things attached, you are in the tetrahedral group. If you are attached to four atoms in three-dimensional space, it looks like this, where this one's projected out into space and this one goes behind. You have tetrahedral. With 109.5 degrees. If one of these occupies a lone pair, then it's still a three-dimensional molecule, and you have a lone pair. This lone pair pushes the bond angle closer, so you get 107 degrees. And so you still have four things. You got three atoms and a lone pair, so there's four electron clouds surrounding it. And the last one is if you have two lone pairs on the central atom connected to two atoms, then you have this is pyramidal. You have bent. Now bent has several different classifications. This is 104.5. This is a traditional one that's like water, where you have two lone pairs and it pushes the bond angle even closer yet. Up here are the three things. You could have a 120-degree bend if the central atom was connected to a lone pair. This happens occasionally. So you got a lone pair and two atoms. Technically, this is a bent with 120 degrees. things that we didn't cover last year. If you have 5 things, atoms, lone pairs, then you have a trigonal bipyramidal. Bipyramidal. You have trigonal bipyramidal. You have the central location being like a flat triangle, but you also have atoms above and below. These are expanded pairs, sulfur and on. The bond angles here are a combination of 90 degrees and 120. This angle here would be 90. This angle here would be 120. So equatorially, it would be 120 degrees. Polar to equatorial would be 90 degrees. This is in itself trigonal bipyramidal. There are possibilities of having lone pairs on this, and one of the favorite ones is if you have a lone pair on one of the equatorial atoms. This actually is called seesaw. Because if you turn it sideways 90 degrees, it looks like a teeter-totter. And it's one that I really like. You can also come up with a T formation, or a T model shape where you have 2 equatorial lone pairs. Here the bond angle would be 90 degrees for both sides. If you have 6 things, this is octahedral. Octahedral is central atom connected to 8 things. These are bigger, these are recessed, like that. So these are out into, and these are recessed back into it. These are 90 degrees totally, all the way around. Octahedral, you can have a couple of lone pairs on this. This is the shape. If you have F6 would be one compound like that. You can have a square planar where the lone pair is down below, and so it forms like a square planar pyramidal. So this is the square pyramidal. And you can have lone pairs above and below, in which case it would be a flat molecule. This is looking down on it. And this is a planar, square planar. These shapes can be explained by just electrons trying to get away from each other as much as they can. There's a theory behind this, is the hybridization or hybrid orbitals. And this works best again with carbon and atoms close to it. Carbon has 2s and 1 p, or 2p. 1s and 2p's. So S2, P2. That'd be carbon. What you can do is you can promote one of these lower level electrons up here, there's a sacrifice in energy, but you get out of it a symmetry. And what you do is you change into 4 equivalent hybrids, which we call sp3 hybridization. So instead of having 2s, 2p, we have 2sp3 hybrid orbitals. So that means they're all the same no matter what. And when you look at these hybrid orbitals underneath a theoretical thing, instead of an s orbital would be spherical, a p orbital would look like dumbbells. A hybrid orbital has a node and an antinode, or a lobe and an antilobe, like that. So they stick out in all directions, and it turns out to be 109.5, which matches up the observation. So this is observational chemistry, and this is theoretical. They're trying to explain why these shapes show up. So this is sp3 hybridization, which is your tetrahedral group. You can have the trigonal planar group. Again, you start with 2s2, 2p2, like this. You promote one up here, but you don't combine all of them. You only combine 3 of them, and you get 3 electron pairs that are the same in a p. So you have sp2 hybridization, 1s and 2 p's makes 3, and a p orbital. What this does is you have 3 equivalent orbitals. This is receding, this is coming out of you. So you got 3 equivalent orbitals, hybrid orbitals. So this is one sp2 orbital, this is one sp2 orbital, this is one sp2 orbital. And you have a regular p orbital, which is dumbbell shaped above and below. If you match that up with another of the same sort, it has a p orbital. And what happens is there is a connection between the 2 here. So this is a single bond, and this is a bond. When you do this straight overlap like this, that's called a sigma bond. A sigma bond is a straight-on, strong sigma bond between 2. And then what happens is the p orbitals, if there's any extra p orbitals like that, they extend above and below. This is one orbital. So this is a pi bond. So a pi bond is a partial overlap between p's, and sigma bond is straight-on orbital between sp or sp2 or sp3 hybridization orbital. I liken this to a hot dog, which is the sigma bond, with the bun. The bun comes in 2 parts, the top bun and the lower bun. So that explains the tetrahedral group. This explains the trigonal planar group, and now the linear group with the carbon hybridization like we do. You have 2 here, 1 here, 1 here. What you do is you move this up, cost of energy, but you get, in between the S and the P, you get two hybrid orbitals and two p orbitals. So you got two p orbitals and you have two sp hybrid orbitals. One of the s's and one of the p's gets together, makes their own type of orbital. They hang around together, make their special thing. What this does is you have your sp orbital overlapping here, then you have your antinode over here, so here's your nucleus, here's your other nucleus. So here you have your sigma bond. Sigma bond right in there. Now you don't have just one p orbital sticking up and down, but you have another one sticking front and back. So you have a pi bond above and below, and in front and behind. So here's your sigma, and you have a pi orbital 1, then you have a pi orbital in front and behind. This is the anti-carb watchers. You have the hot dog, and you got the hot dog bun above and below, and let's throw on another hot dog bun. You can't get enough of those carbs, so you get two hot dog buns surrounding it. So you got a bun above and below, and in front and behind the hot dog. This works very well explaining very small, simple molecules. Things that involve carbon. They did have nitrogen, oxygen, things in that same period, second period of the periodic table. They did have a question on below nitrogen's phosphorus. Phosphorus, nitrogen, if it has NH3, will have a pyramidal shape. Pyramidal shape, and the bond angle is 107 degrees. If you have pH3, it is almost a 90-degree angle. So there's hardly any hybridization going on. It's 93 degrees angle. So there's a little bit of separation, but not much. It's almost like it's so large of an atom, the hydrogens can't interact with the other atom. Now if you have nitrogen, which is a smaller atom, the electron clouds push, so it spreads out. But since phosphorus is such a big atom, there's hardly enough space for the two electrons in the hydrogen atom to push out away from each other. So the hybridization as you go down the periodic table decreases until it's almost indistinguishable from the above. There is the newest, which is also the most complicated, the molecular orbital theory. And we're just going to basically say it exists, and it's a better model, but it's more complicated. And we are not required to get into it, how to do it or anything else like that, but all we need to do is kind of define it. So the MO theory is a better model, it's more complicated, and what it does is instead of having hybrid orbitals on an atom, they do hybrid orbitals on the molecule. Molecular orbit theory, MO. So, and it's very confusing. They got nodes and antinodes and all sorts of things like that. It is a better model. It's more complicated. You can't really calculate anything, even with supercomputers. What you got to do is you got to make an assumption and then run a test and see if it gets better if you jiggle it one way or another. So it's by trial and error that you get these things yet. So we haven't come up with any theoretical basis on it, but when you do get the computer programs that work on it, it does give a better explanation of what's going on. Specifically, they explain why oxygen is paramagnetic. Paramagnetic means it acts like a magnet in a magnetic field. If you look at hybrid orbital or Vesper, it's a symmetrical molecule, so a magnetic field shouldn't affect it at all. If you put oxygen or liquid oxygen in a magnetic field, it does all sorts of weird, fancy schmancy things. But it does do a better job explaining. It's a better model, and instead of having the electron cloud being centered between two atoms, the electron cloud is centered on the entire molecule. That's all you need to know about molecular orbital theory. That's it on this lesson on shapes of molecules.